repeat or?
Yeah.
Do you want me to repeat from zero so that you can record?
I want to record your talk, all the talks. Yes.
Yeah. Do you want me to repeat from zero, or are you okay?
No. It's okay.
Yeah. Okay. Okay. Yeah. Yeah. Anyway. Yeah. So So maybe like for the recording. Yes. I would like to, as I said, this is the first time about this. I would like to argue for this interface between machine learning, dynamical system, and AIT. So machine learning and dynamical systems, we are clear why it's important. Machine learning and AIT, it's slightly gaining momentum, especially that we heard the head of OpenAI last year, I think, where he said that the secret behind GPT is kernel complexity. They didn't say why, but somehow I also would like to argue for that because somehow some people argue that one of the weaknesses of machine learning is that it's over relying on statistics. It will be nice to try to reformulate machine learning methods using methods from algorithmic information theory. And that's what I'm trying to do here, using reformulating sparse kernel flows as a method, as an AIT method, where we use Kolmogorov complexity to argue that learning kernels from data using sparse kernel flows is consistent with the AIT. And also the other direction that I have been working on slowly during the last 2-3 years is the interface between dynamical systems and AIT. So I'm going to talk a little bit about this, but today I'm just going to focus on two main problems, which is reformulating a machine learning method that is learning kernels from data using sparse kernel flows as an AIT problem without needing to use cross-validation. And the other problem is to look at problem of simplifying PDEs using kernel methods and showing that this is consistent with the MDL principle. That is one of the important principles in AI. So so as I mentioned, so the gap between machine learning and dynamical systems is important to feel, and then the clear directions are machine learning for dynamical systems, where the goal is to analyze dynamical systems on the basis of observed data rather than attempt to study them analytically. So this would allow to extend the boundaries of the classical theory of dynamical systems. Other directions is the dynamical system for machine learning, where the goal is to analyze algorithms of machine learning using tools from the theory of dynamical systems. So here we want to look at algorithms of machine learning as dynamical systems. And here we want to, this would give like solid foundation of the existing method and understand their true potential and limits. The other gap that I'm arguing for, and as I said, it seems quite timely, especially the popularity of GPT now, and then the statement that was made last year by the head of one of the chief scientists of OpenAI, where he said that the secret between behind GPT is kernel complexity. So here I would like to argue for to fill the gap between machine learning and AIT in the following directions. Machine learning for AIT. So here we want to look at applications of Solomonov induction, algorithmic probability approaches to probability predictions, and the links between information learning and data compression in view of developing or using machine learning algorithms for better compression or prediction of prediction. And eventually the goal is to approximate kernel complexity using machine learning methods. I mean, that's still like goal that is hard to reach, but it's good to keep this in mind. The other direction is to look at algorithmic information theory for machine learning, and that's what I'm going to talk about. So here I want to look at the domain of applicability of certain machine learning methods and explain, for example, why certain methods in machine learning will work a priori so well for certain problems. You see here the keyword is a priori. So there are methods here in machine learning that will a priori work or a priori will not work, and this would be independent of the method itself. So here IT is part, in a way, it's the computational part, is a computational part of information theory. So it looks at data as such. So we want to look at what data can tell us about a complex system and see if this will lead to certain conclusions, whether they are positive or negative, but again, it's a priori. So the part of machine learning dynamical systems, so this is like Steve Smale already saw it about 15 years ago. So that the unification of dynamical systems and learning theory is a major problem. And it's important to develop a comparative study of useful algorithms currently available and give them unity from the dynamical system perspective. And I think I mentioned this before, is that this is how I got involved in the field through the encouragement of Steve Smay, indirectly via a friend of mine, a colleague who was doing a postdoc with him. So he encouraged both of us to work on this interface. And yeah, this is how my journey in machine learning and dynamical systems started. And this is what we brought, yeah, about almost 10 years, yeah, more than 10 years ago, where it is easier to simulate dynamical systems and analyze the empirical data rather than attempt to study them analytically. But the mathematical theory necessary to analyze dynamical systems on the basis of observed data is still largely undeveloped. And as I mentioned, during the last 3 years, somehow I started being interested in AIT. And this, for example, what we wrote, that we proposed to adopt a probability complexity perspective on analyzing dynamical systems, because this would enrich the statistical learning theories related to series prediction and analysis. So it not only facilitates a deeper understanding of simplicity bias, I mean, that's like one of the concepts in AIT and its implications, but also paves the way for novel methodologies in forecasting complex systems behavior, especially in cases that are dominated by uncertainty and stochasticity. So we already have 3 papers about this. And like the latest one, which is about bridging AIT and machine learning via Sparse Kernel Flows, where we say that this approach opens the door to reformulating algorithms in machine learning using tools from AIT with the aim of providing them a more solid theoretical foundation. So here we try to get rid of regularization in machine learning. That seems to be one of the weak points in machine learning. Yeah, so the talk will be divided into 2 parts. First part is introduction to kernel methods, and then we'll talk about Sparse Kernel Flows as a method to learn chaotic dynamical systems. And then we'll look at the MDL principle as a way to reformulate Sparse Kernel Flows and show that Sparse Kernel Flows is the best method to learn kernels from data, and that it is consistent with Kolmogorov complexity. Second part is to look at the problem of simplifying nonlinear PDEs, and we would like to argue here. So we are going to use the Kohlhoff transform as a way to argue, but the goal is bigger. So we are going to use Sparse Kernel Flows to learn the Kohlhoff transform, and we want to show that the fact that we have Sparse Kernel Flows that allows to reduce the number of data points and the number of parameters that allow to simplify PDEs, and the fact that we simplify the PDE makes it consistent with Occam's razor. And so this means that we are going to be consistent with the MDL principle. So I'm going to give a quick overview of kernel methods so that we are on the same page regarding what Sparse Kernel Flows is about. So the kernel methods appeared in the 30s as an answer to the question, when is it possible to embed a metric space into a Hilbert space? So if the metric satisfies certain conditions, it is possible to embed a metric space into special kind of Hilbert spaces that are called the producing kernel Hilbert spaces. So they are essentially Hilbert spaces with two properties. The producing property, that is the one that is here, and the second one is that the reproducing kernel has a span that is dense in H. So in another way, RKHS is a Hilbert space of functions where all evaluation functions are bounded and linear. So important properties of reproducing kernel is that the RKHS is unique. We have symmetry, we have positive definiteness, and then we have the cause of the decomposition of the kernel as an inner product in H. So this leads to the canonical feature map, which is PCX equal to KX dot. So then you have the popular kernels like the monomial, Gaussian, and hyperwidth tangent. So one of the applications of RKHS, the popular ones, is the e-learning theory, where the goal is to find an unknown function from random samples. So the goal here will be to minimize this functional here. So since rho is n-known, then one goes to an approximation. So you see here, you see the key is, yeah, so we assume that there is a rho But as we'll see later, that we using AIT and the MDL principle, there is no need actually to assume that there is a row. So this is one of the things that can be skipped using AIT. So the error E is approximated by, so it's discretized, and then it's going to be approximated by the following sum plus regularization parameter. So here you see there's always the regularization that appears. And using AIT, we want to argue that this regularization parameter from deeper perspective is coming from a compression algorithm, compression perspective using Kolmogorov complexity. So this is what we are going to illustrate using Sparse Kernel Flows. Yeah, okay, so here, so this minimization is taken over functions from hypothesis space, often taken to the ball of the RKH as HK associated to a kernel K. And the function Fs that minimizes the empirical error S is the sum of Cj, Pjx, where Pj is the feature map, and the Cj, the satisfied system of linear equations. Okay, now the natural question is always how to find the kernel, and so this is where kernel flows come in. So if we want to try to approximate an unknown function from random samples, in the setting of optimal recovery, this problem can be turned into a well-posed problem by restricting the candidates for U to belong to a binary space B with the following norm. And this can be viewed as an optimal recovery problem that is a minimizer of the following relative error. So mean of V, max of U minus V square over U square. And so the method of kernel flows is based on the premise that the kernel is good if there is no significant loss in accuracy in the prediction error, if the number of data points is halved. So, so this is important because this is what is going to allow us to get into AIT, because you can look at it from different perspectives. So you can say that the kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. But we can also say that if we are able to minimize the number of points that we are using, meaning that we compress the information that is contained in data, then we are going to get a good kernel. So you see, we can see look at kernel flows from this perspective, that either we start by minimizing the number of parameters given the number of points that we have, or we try to minimize the number of points that we have in view of finding a good kernel. So this led to the introduction of the following relative error. So where V, which is the norm of V star minus Vs over V star squared. So V star is the optimal recovery based on the full number of points versus half of the data points. So how does it work in practice? So we have our data set. So we take a random sample of size n, and then from it we take a random subsample of size n over 2. And then we use the relative error that I just talked about. We can reformulate it as follows. And then we evolve theta in the gradient descent direction of rho, that is theta k plus 1 is equal to theta k minus delta gradient of rho with respect to theta, and repeat. So we apply this to chaotic dynamical systems. If we have a time series in RD, our goal is to forecast xn plus 1 given the observation of x1 to xn. So we can view this as a regression problem. So learning F dagger that maps zk to zk minus tau dagger plus 1 to zk plus 1, and we solve this as a regression problem between codes. And so we have an approximation fx is equal to kxx plus times the k capital X minus 1 times y. And we introduce, I think I already talked about this before, and probably even in the last edition of this conference, we introduced various variants of kernel flows. So this is the relative error. Another one is based on the Lyapunov exponents, and where we are interested. So the first one is based on short-term prediction. Second one is based on long-term prediction. Another version of kernel flows is based on the maximum mean discrepancy, where we are looking at statistical properties. And another one is based on the Hausdorff distance, where we say a kernel is good if the Hausdorff distance between the construction of the attractor with capital N points versus capital R over 2 doesn't change much. In a way, so this is like more of a geometric argument. So everything I'm going to say about sparse kernel flows, in a way, we can change the first term and then use any of these terms here. So the relative error that want to show up afterward is not very important because it can be replaced with any of these. So Sparse Kernel Flows is based on the following things: that we take a large dictionary of kernels consisting of m elemental kernels, so the sum of theta I squared ki xy beta, I varying from 1 to m. So we want to sparsify chi beta theta by L1 regularization. So that's the relative error that we had before, 1 minus one of these terms here. But as I said, so all of these, I mean, they can be replaced. So by rho L, rho MMD, rho HD. So this term here is not really important. It can be replaced by the other variant. And so the key here is to look really at class lambda norm of theta 1, the L1 norm of theta, and where is it coming from, and then what does it really mean, and if there is a deeper understanding, a deeper interpretation of this term. So apply this to a database of 131 chaotic dynamical systems to show that it effectively works. So we use this kernel that we just basically developed it using different toy models that in previous papers. So this is an example of one of the examples in the database. So here is the reconstruction of the attractor. This is like another example. This is the reconstruction of the attractor using Sparse Kernel Flows. And these are the errors, like regular Kernel Flows versus Sparse Kernel Flows. You see that the errors are being decreased, whether in SMAP, which is like the predictions error in the time series, versus reconstruction of the attractor. So see, in all cases, we have drastically that. Yeah, okay, so now let's look at the IIT point of view. So within computer science, algorithmic information theory directly connects computation, computability theory, and information theory. Machine learning and information theory are two sides of the same coin. The central quantity of algorithmic information theory is Kolmogorov complexity, which measures the complexity of an individual object as the amount of information required to describe or generate X. Technically, Kx is the length of the encoding of the shortest program key that produces X when given as an input to the universal reference Turing machine. So that's the formal definition of Kx. So where U is the universal reference Turing machine, and length P is the length of P in binary representation. So here, there have been proofs that actually implementing on the universal reference Turing machine or the code that we are using, the language program that we use, actually do not change match Kx. There is just a coefficient that is added. So yeah, so when we say universal reference Turing machine, you don't have actually to get distracted too much about it. For example, see if X contains repeating patterns like 1, 0, 1, 0, 1, 0, you see then it's easy to compress, and hence K of X will be small because you can write a program that says repeat 1, 0, 10 times. So that will be the shortest program that you can write, whether in Python or Julia or whatever computer language you are using. On the other hand, if you have like a randomly generated bit string of length n, then it's highly unlikely to contain any significant patterns, and hence can only be described by specifying each bit separately without any compression. And so the Kolmogorov complexity will be approximately equal to n bits. So intuitively, there is a link between Kolmogorov complexity and kernel methods. Kernels are a measure of similarity, and if two objects are similar to each other, then they can be compressed. And if they are not similar, then they cannot be compressed to each other. So a reasonable definition for the similarity between two objects is how difficult it is to transform them into each other. So, and this leads to the conditional Kolmogorov complexity. So the length of the shortest program that computes X from Y. So this is the formal definition, is that if you have a program where you are given Y, can you generate X based on that? So if Y is n-informative or n-related to X, then Kx given Y would be essentially the same as Kx, which is the Kolmogorov complexity of X. However, if Y contains a lot of information related to X, then Kx given Y will be significantly smaller. And this is where I see the link with kernel method. So now the minimum description length principle provides a criterion for the selection of models, regardless of their complexity, without the restrictive assumption that the data from a sample come from a true distribution. So you see here, when I talked before, when we're trying to talk about learning an unknown function from random samples, there was always an underlying assumption that we know that the data are coming from a distribution here, from distribution. Here, there is no need. So the minimum description length principle doesn't really require this assumption. So it can be here, the MDI principle can be viewed as a downscaled practical version of kernel of complexity. So the MDI principle recommends to use among competing models the one that allows to compress the data plus the model most. So and this is where this is what I'm going to use to illustrate, to justify that sparse kernel flows is the best way to learn kernels from data, especially in the context of learning unknown functions from random samples. And two, in the kernel context of simplifying PDEs from data using the transforms that are learned from the data, and where the model is the simplest and ideally linear. So the better the compression, the more regularity has been detected, hence the better the predictions will be. So the MDL principle can be regarded as a formalization of Occam's razor, which says to select the simplest model consistent with the data. The MDL principle says that the best model is the one which permits the shortest encoding of the data and the model itself. It is the addition of the code length for the model which separates this principle from the familiar maximum likelihood principle and makes it global in the sense that any two models, regardless of their complexity, can be compared. So here you see we are going slightly deeper than the maximum likelihood principle and the Bayesian approach, in the sense that there is something called the universal prior or the best prior, which is the based on something called the Solomon of induction, where the prior is algorithmic probability, which is given by 2 to the power minus Kolmogorov complexity. So, for example, let's consider that we have a set Q1 to Q2, etc., of countable class of models or theories or hypotheses, or even probabilities over sequences, sorted with respect to their complexity K of Qi, containing the unknown true sampling distribution P. So for finite X, let's Qix be the Qi probability of data sequence little x in capital XL. So it is possible to code X in log Px minus 1 bits using Hoffman coding. I mean, these are things I'm still learning myself. So, but so this is, but it seems that it's possible to find the length of the code based on the on P. So since X is sampled from P, then this code is optimal. So, but since we do not know, we could just select Q in M that leads to the shortest code on the observed data. And in order to be able to reconstruct X from the code, we need to know which Q has been chosen. So we also need to code Q, which takes K of Q bits. And hence, X can be coded using log, the Q that minimizes log of Qx plus K of Q bits. So you see here, we are already seeing a method that allows to select the model. And that's exactly what MDL does. So it gives us the one that minimizes the log of Qx plus K of Q. And you see, this is closely related to Bayesian approach, as I mentioned. So the Bayesians use the base of Z given X for the prediction, where base is the Bayesian mixture with prior weights WQ. And for MDL, WQ is 2 to the power minus K of Q. So here I'm just going to compare between regularization in machine learning and AIT. So the classical approach in machine learning to combat overfitting to a too complex model is to add the regularization term to the loss function. So here you see, so 1 is given, is the argument of F. Yeah, okay, I should have written this equation here, but I said this is the first time talking about this. I hope you forgive me for still not having very clear slides. So you see F star is the argument of loss of Fxt yt plus lambda R of F. But you see the MDL principle is argument of log of Q plus K of Q. So one, in a way, the MDL principle is imposing a log of Q of X loss, while the other one, the loss can be as general as possible. while the regularizer in machine learning is lambda R of f, so we need the regularization parameter, while in MDL, we have K of Q, which is related to Kolmogorov complexity. So in a way, so this is how there are slight differences between the two. So the MDL principle is completely general. It makes no assumption whatsoever on the underlying border class row, no IID or stationarity or ergodicity or parametric or smoothness assumptions, while regularization in machine learning is somewhat tailored towards IID data. MDL is limited to log loss, while any loss can be used in RML or regularization machine learning. RML requires choosing a penalty R and tuning its length lambda, often by cross-validation, while MDL theory dictates the penalty term, so there is no need to use cross-validation, there is no need to choose lambda. So these are the two parallels, but this also allows us to reformulate sparse kernel flows. So remember, we said that our goal is to learn a kernel of the form sum of theta I squared k I x y of beta. So using an MDL principle, so we want to minimize the loss. So as I said here, the first one minus the numerator divided by numerator is really secondary because it can be replaced by the other versions of kernel flows that we talked about. But here, the MDL principle dictates that we are going to have the following penalty term, which is P over 2 log n. So P over 2 log n is the one that allows us to have combinatorial problem to find the best term that minimizes Kolmogorov complexity. So we want to compress the data. So this leads to solve 2 to the power m optimization problems corresponding to the combinatorial problem where one solves m minus p out of m of the theta I set to 0. But you see, in practice, what's going to happen is that we are not going to solve this very large optimization problem. We are just going to get to a surrogate loss, which is exactly what we introduced in Sparse Kernel Flows in the version I talked about at the beginning, where the penalty term is lambda L1 penalty of L1 term of theta. Sorry, do you have questions? Hello? Okay. So this also penalizes the non-zero parameter, but any amount proportional to its magnitude rather than log n over 2. And this has also the advantage of being convex. So replacing the MDL regularizer by the L1 regularizer is a form of surrogate loss, so that is popular in machine learning, but for the regularization. So the general idea of surrogate loss is to replace the loss one cares about with a different surrogate loss, usually convex, that is computationally more convenient. And this is exactly what we showed here. And hence, sparse kernel flows is the natural way to learn kernels from data. There is no need to use cross-validation to justify its efficiency, and everything follows from AIT. So the fact that sparse kernel flows considers that a kernel is good if the number of points can be halved without a loss in performance plus reducing number of parameters in the coefficient shows that it is consistent with AIT. And here, actually, we even conjecture that the minimal number of points that we are using in sparse kernel flows are the covering numbers that show up a lot in kernel methods. And that this would give us the best performance. So the covering numbers plus, so if we combine between covering numbers and the sparse kernel flows, then the conjecture is that Kolmogorov complexity will be minimized. But again, it's just conjecture, so there is still work there. So how much time do I have left? Is it 10 minutes, right? Or 15 minutes?
You have 15 minutes.
Okay. So maybe I went too fast here, but anyway, so it gives me some time to talk about PDEs. Yeah, okay, so here, as I said, so I'm trying to build an argument based on different little things. So then I'm going to start the second part, which is simplifying PDEs using kernel methods and an AIT perspective on that problem. So, okay, let's look at just come a step back and then go back to our courses on PDEs. So linear PDEs, we now have wave, heat, diffusion, linear Schrodinger. Nonlinear PDEs, popular ones are KDV, Burgers, parameter Sipashinsky, Fisher, Kolmogorov, etc., etc. And the question is, can we construct a framework for transforming any nonlinear PDE into linear PDE? And if not, and we know that this is not going to happen, at least simplify nonlinear PDEs as much as possible. I mean, one of the reasons we know that it's not going to happen is that if you take Kuramoto-Sifajinski, so there we have chaos, and you cannot map a chaotic PDE, but it's PDE with chaotic behavior to a linear PDE where there is no chaos. But at least we want to see if there is a way to map nonlinear PDEs to simpler ones. And we'll focus on call hop. So this is, as I said, this is like still work in progress. So this is why I wanted to talk about it, just to see if there is feedback from the audience. And we want to, so we know that analytically it's hard to derive this kind of transforms. So this is where we want to argue that we want to use kernel methods to do that, and then put on top of it sparse kernel flows in a view of learning the kernel that allows to simplify PDEs. And so why is it important? Because nonlinear PDEs are harder to solve and interpret. Nonlinear PDEs can exhibit chaotic behavior, so it's easier to compare, to analyze dynamics of linear PDEs versus nonlinear PDEs. And closed form transformations between nonlinear and linear PDEs are hard to find analytically, and so we want to propose to do that using kernel methods. Yes, the call hop. If we take the viscous Burgers equation, Vt plus nu plus Vvx equal to nu Vxx, and the heat equation is Wt nu Wxx. So call hop is allowing us to transform one PDE to the other. So V is equal to minus 2 nu Wx over W, or you can have the you can express W as in terms of V. So these are call and hop. So okay, now let's see how we can do. So we want to skip the analytic part. So let's consider B and H to be the forward time solvers for Burgers and the heat equation based on the earlier method. But again, any other integrator can possibly be used. Here we just focus on Euler because it's just easy. So we have V1 is equal to BV0. So this is the expression. W1 is equal to HW0. And this can be written as the discretization of the equations. There's Z naught by P to be the integral operator that maps V to U. And so we see that we can reach W1 from W0 in two different ways. So W1 is equal to H dP V0 and W1 is equal to dP V0. So we can represent this as in a diagram. And that's exactly what's happening here. So we have this diagram, and we want basically to make sure that we reach the same point from the two sides. And this is how we are going to learn the call hop transform using kernel methods. Okay, so what is the optimization problem here? Is that we want to minimize the RKHS norm of D such that we have the constraint that we had before. So DP. So we are looking for D, that D here, that appears in the first direction and also in the second direction. So we want to minimize the RKHS norm of that versus that dP, dP V0 is equal to W0 and dP V0 is equal to W0 and dP V0 is equal to SW0. And D0 is equal to 1, D of 1 is equal to 0, just to enforce uniqueness. So now, I mean, we have this constraint here. We ideally want to aggregate the constraints and then introduce the phi, which is equal to HFPV0 minus FPV0. So D is going to be the fixed point for phi. So phi of D is equal to 0. Modulo D of 0 is equal to 1 and D of 1 is equal to 0. So so these are just like technical things. And so the thing is, luckily, I mean, using kernel methods, we can solve the previous optimization problem using a generalized representative theorem, KU phi tilde, KP tilde, P tilde minus 1y, where phi tilde are the generalized are derivatives. So this is just like the representation of the terms in the representative theorem. So this is just like the explicit form of the D. So then we implemented this on the Berger's equation with 101 qualification points and following initial condition, and we used kernel flows at the following laws to learn the transform. And yeah, so that's what we get. We get the recovery of the heat equation, recovered blue, true, orange, and learn call hop versus orange is true, recovered is blue. Then we add noise. And we see that if you add noise, then you see it's slightly sensitive to noise. So if noise is small, then recovered versus true, the gap, so initially is going to be large, but then it converts. If you increase the noise, then you see the gap is getting larger and larger. And so you see this what's happening: 10 minus 1, 10 minus 10 minus 2, 10 minus 1, etc. We also looked at different kernels, so exponential versus Gaussian, Mattern, inverse quadratic, etc. And there it becomes evident that learning the kernels is important, and this is where sparse kernel flows comes in. And so if we look, for example, at the following kernel, Gaussian versus Laplace versus inverse quadratic, the goal is to apply sparse kernel flows to learn the call hop transform in view of simplifying the nonlinear PDE into a linear PDE. So that's the loss, and so that's about it. So then we argue on that this is consistent with MDL. So that the problem of simplifying PDEs using kernel methods is consistent with the minimal description length principle, since we are using the simplest model as a target, which makes it consistent with Occam's razor, and minimal number of points, since we are using sparse kernel flows. So we again remember if we look at sparse kernel flows from the MDL principle, we are not saying exactly the main the statement that we were making about sparse kernel flows. Kernel is good if we are able to reduce the number of points without losing accuracy. Here we are doing it the other way around, in the sense that we want to compress the data we are using in view of learning the kernel. And this is where Kolmogorov complexity comes in. So first we look at the data, we reduce the number of data through compression, then you learn the model. So here, this is what's happening here, right? So we are, in a way, we are combining between finding a transform that allows to reduce the number of points and simplify the model, because the target is to simplify a PDE, to get the simplest PDE. And in our case, it's a linear PDE. Conclusions. So we introduced the method of sparse kernel flows and showed that it is efficient in learning a large database of chaotic systems. We reformulated the problem of learning kernels from data using the MDL principle. We showed that the loss involved in the method of sparse kernel flows can be viewed as a problem of data compression, and that the problem of learning kernels from data using kernel flows can be viewed as the problem of choosing the shortest description where the MDL principle can be applied. The point of view allowed to prove that learning kernels from data using kernel flows, and in particular sparse kernel flows, is the natural approach to adopt and is consistent with Occam's razor. This allows to show that it is not necessary to use a cross-validation argument to justify the efficiency of kernel flows, thereby illustrating that we do not have to go through the statistical route, and we can directly work with code lengths and complexities. Same way of thinking applies to simplifying or linearizing ideally PDEs. Sparse kernel flows to learn the kernel, to learn call hop, then mapping to a linear PDE versus or simpler PDE where the complexity is minimal, since the solution is now. So if we have like linear PDE, then it's ideal because we know the solution, and so it's not even necessary to add an extra level of complexity. So our ultimate goal is to reformulate other machine learning and dynamical systems problems from an AIT point of view, in view of giving them a more solid foundation. And these are like some of the references about this. Yeah, some are, yeah, most are, yeah, all of them are online. Yeah, some of them, actually, yes, yeah, some of them have been accepted and others are under review. Yeah. All right. Okay. Thank you for your attention. So I think I just made it on time. Yeah. Thank you.
Thank you very much again for that great talk. Other questions, comments? Yes. So Hirotada, please.
Okay, so thank you for your great talk. Okay, thank you for your interesting talk.
Thank you.
And I have some questions.
Uh-huh.
The first one is, yeah, you mentioned in your conjecture that the minimum number of necessary points might be the covering number. And we often use, yeah, this quantity, covering number or bracketing number that can be connected with Rademacher complexity or VC dimension as well. So what do you think about the link or connection between Kolmogorof's complexity and covering number, for example? Because I'm not sure with Kolmogorov complexity.
Yeah, so this is where I said that this is what I'm still part of a conjecture, so I need to think more about it. But I guess that, yeah, as I said, the way I view it is that if we start from the covering numbers, then you see it will be the complexity. So we cannot compress further, right? So if we start from the covering numbers, that there is no way to compress further, and therefore this is where the complexity will be minimal. So if we have other points that are more than the covering number, then the goal is really to reduce the covering numbers. And in a way, I'm conjecturing that if you start from covering numbers, then this is the minimizer of complexity. Yeah, just remember this. Why I said like it's worth exploring the direction IIT machine learning, and one of the conjectures through this work is that that covering numbers will minimize complexity, and that there is no way to go below.
Okay, thank you. I have one more question. It's often important to measure the complexity of, for example, hypothesis sets. And we often use the indicators that I mentioned before. But I also think that, yeah, from some arguments with our students, for example, if we consider a space of graphs, for example, we should identify some identical graphs. So in that case, we should consider the space of equivalence class, for example. So in that case, we should consider the data sets on some manifold. So we often think that recently, we should also think about the manifold where the data set or population distribution lies. So how do you think about this?
Yeah, that's a very good comment. Yeah, please send me the email because I would like to talk to you more about this. Because you see, but here when we introduced MDL, this is a very good comment. So when we talk about MDL, you see, M contains models, theories, hypotheses, probabilities. So it includes everything, right? And if you know that your data are lie in a manifold, then of course you need to take this into account because it will allow you to compress your model. So your resulting thing. That's definitely that's a very good comment, and I totally agree with you that if you know that data are in a manifold, then that's something that will allow you to compress remember when we talk about compression, we can think about it as writing a code, right, in a computer. And if you say I know that my data are in that manifold, then you see the code will be much simpler. So that's definitely I agree with you. I think that this is very very relevant. But I'll be happy to talk to you more. Please send me an email. I said I'll be happy to talk to you. I'll be happy to talk to you more about this. If you can send me an email or if you can write your email, I'll send you an email.
Okay, thank you. Thank you very much.
Thank you.
Other questions? There is a comment on chat.
Okay, let's see. So thank you for your thoughts on the thing for long period of time. This for non-consistent feedback. Yeah, that's a good question. Yeah. So I would say, yeah, I would say that MDL and yeah, kernel complexity would allow to do that because the kernel, yeah, with the MDL principle is a solution to the problem of yeah, overfitting. And I guess that this inconsistency that you are talking about, I'm not very good to understand what pins are about. Yeah, I think feel free to send me an email as well, and I'll be happy to talk to you more about this. But yeah, from what I understand is that, yeah, I would say yes. I would say that it is possible to solve this problem of inconsistency of pins over long period of time. But yeah, but we need to talk. Because as I said, I mean, you need to tell me exactly what the problem is there, and then we can think about it. Yeah, thank you. Yeah, I'm just talking about from intuition here because but I guess that this would be this would help there as well. Yeah.
Okay. Thank you very much, for the nice talk.
Yeah, thank you very much. Thank you.
Okay, let's move on to the